Calculus is based on a concept that we call a limit. And the idea of a limit is something that you can get really close to, but not get to. So here we have a sequence. 8, 4, 2, 1/2. What would be the next number? 1/4. If you kept on going, what value would you get close to? You would get close to 0. Would you ever be exactly at 0? No. Okay? But we would say as this gets bigger and bigger and bigger, this gets close to 0. And we would say that 0 is the limit of this sequence. Some notation stuff that we have here, we can n arrow infinity means as n approaches infinity. In other words, as n gets very, very big, the sequence, un, gets close to 0. And so we would say the limit of this sequence is 0. It's never equal to 0, because you could always get, cut something in half and then have a little tiny bit and cut it in half again and have a little tiny bit. But it becomes as close as possible to 0. In other words, if someone says, there's a value you can't get closer to 0 than 1 over 10 million. And you just say, well, I cut it in half again, and now I'm closer than that. Well, what about 1 over 10 billion? Well, if once I get close to 1 over 10 billion, I cut it in half again, and now I'm closer than that. And so we could get as close to 0 as we wanted to without ever getting to 0. Does that make sense? So we call that arbitrarily close. So we would say that the limit of this is 0. And we did geometric sequences like this. Yeah, and even infinite geometric sequences of adding this up. So an example of adding this up is I could start 16 units away from, or 16 tiles away from the wall. And I could walk 8 tiles, and now I'm 8 away from the wall. Then I could walk 4, then I could walk 2, then I could walk 1, then a half, and then a quarter. And if I added those all up, you can see by my walking, I'm going to get really, really close to the wall. Will I ever touch the wall? No. But the sum of that infinite sequence would be 16. I mean, you've got your formula. Term 1 is 8 over 1 minus r is a half, and that's equal to 16. Now, we were using the idea of a limit already in geometric sequences when we added up to infinity. Do you actually ever walk 16? No. But you get as close to the wall, arbitrarily close, once you kept on doing it forever, that we basically say, you're close enough, we're going to say that it's equal to 16 because it's arbitrarily close to 16. So as n goes to infinity, the sum of those terms would be 16. We can say the limit is equal to 16. Now, when things have a limit, or for sequences like that, we call those sequences convergent because the values came to a certain number. And that number that it comes to, we would call the limit. Here's some notation for you. So when we write limits, we use LIM, short for limits. Underneath, we say, what is the idea approaching? In this case, n is getting bigger and bigger. The term in the sequence then, as n gets bigger and bigger, is equal to 0. And we could write the limit for the sum. It would equal 16. Sequences that do not converge are called divergent, and there we say the limit doesn't exist. Look at this pattern of numbers. What's the next number? 0.2222. What's the next number? 0.22222. To what number does this sequence converge? What? It's not infinity. You think it like gets close to 10 billion? No. What would you say, right? If we call this sequence UN equals U1, U2, U3, the limit as n goes to infinity for UN would be 2 over 9. And how did you get 2 over 9? What's another way of writing 2 over 9? 0.2 repeated. Can you see eventually you would have all the 2's? Now, we'll leave it at that. There's some fun stuff that we could do with geometric sequences, but we don't need to right now. So this sequence does converge, and it gets closer and closer and closer to 2 over 9. Oh, do you want to see the geometric sequence proof of this? Okay. If I change these, if I write the following sequence, 2/10, 2 100ths, 2 1,000ths, 2 10,000ths. Can you see that if I added this one and this one together, I would get the second one? If I added the first 3 together, I would get that one. Can you see in this sequence that it's geometric with r being 1/10? And if you added them all up, your sum to infinity would be my first term, which is 2/10, over 1 minus r, which is 1/10. And this would be 2/10 divided by 9/10. And if you simplified that, you would get 2 9ths. And you can do this with any repeating decimal if you want to find the fraction, which is kind of cool. Okay. Limits of functions. What is the limit as x gets close to c of a function? And what we're looking at is, and some functions are going to be really, really easy to find. So I'm going to do a really simplistic example of a function. Here's my function, y equals 2x plus 1. I can even label it with function notation. F of x is equal to 2x plus 1. It has a y-intercept at 1. It goes up to over 1 for our next point. It's just a straight line. Our question is going to be, what is the limit as x gets close to 1 of f of x? So what we're wondering is, as I get close to 1 from this side, what does my y value get close to? This isn't extraordinarily hard. Would you say that I'm getting closer, it's going up and it's getting closer and closer to 3? And if I came at x from this side, my y values would be going down, and would you say that they're getting closer and closer to 3? And so we would say the limit as x gets close to 1 of this function is exactly the same as plugging that value in. It's equal to 3. And it is just like plugging that value in. In fact, most of limits you can do that. If you can plug the number in, it's going to equal that. However, there's going to be some times that you're going to get functions that are broken up. Maybe they look like this for one part of the function and like this for another part of the function. So if this blue graph is my function, does it make sense? 1, 2, 3. Does it make sense that when I plug in 1 according to the graph, it's equal to 3? Because that's the point that's filled in. The open circle means that f of 1 is not equal to 1. But on this graph, we would say our limit as x goes to 1 of this function, f of x, does not exist. Because if you approached 1 from the left, you would say it's getting closer to 1. But if you approached the x value of 1 from the right, you would say it's getting closer to 3. And since the left side and the right side don't match, then we say the limit doesn't exist. In order for a limit to exist, it's got to approach the same fixed value from both sides. So you can get some interesting situations. You can play around with graphs and have some weird situations, but often what we're going to be looking at are the graphs in grade 12. You remember the graphs that had holes in them? Those are usually the questions that you're trying to find the limit of. And so we'll get to some of those in a second. So here's our graph of x squared. What happens as you get close to 2? It's going to just equal 4. In fact, any graph or any equation where you can just plug that value in, it has no non-permissible values, the limit is going to be just what the value you'd plug it in for. Can you see on this one that as you approach it from this direction, it gets close to 4, and as you approach it from that direction, it approaches the same number? We're going to find out that if your original function is continuous, meaning that we can draw it without having to lift our pencil, then you can just plug the value in to find the limit. And it's that straightforward. So the graph approaches 4 as x approaches 2 from both sides. So you can look, what happens as I get closer and closer to 2 from the left side? You can see my numbers are getting closer and closer to 4. And if I look at my table of values and went closer and closer to 2 from the right side, it gets closer to 4. From either side, it gets closer to 4. But it's going to be just as simple of, you're going to ask to find that limit. If you can plug the value in, and you know that your function is a continuous graph, like a parabola, it isn't broken up into a bunch of different pieces, then you can just plug that value in. Now we get into a situation where when we graphed this in the past, x squared minus 1 over x minus 1, this was an example of a graph with a hole in it. Do you remember how you could tell if a graph had a hole in it? If I had f of x equals x squared minus 1 over x minus 1, and if I could factor the top, in this case it's a difference of squares. Do you remember that if one of your factors canceled out, if a non-permissible value canceled out, that meant there was a hole in the graph? That was like chapter 1 of grade 12. No, chapter 2 of your textbook in grade 12. And so this graph has a hole in it, and this should be drawn, when you draw a hole in your graph, it's with an open circle. And you found the value of that hole by, after simplifying, plugging in x equals 1. And so you'd have 1 comma 2. Now, since it approaches 2 from the left and it approaches 2 from the right, we would say that the value of the limit is equal to 1. Numerically, we can see this as well. So even though this function is not defined at x equals 1, we would say that the limit does exist and is equal to 1. We're going to do one more example. This is called a piecewise function because it's defined in 2 different pieces. So the function f of x is equal to 1 when x is bigger than or equal to 0, and it's equal to -1 when x is less than 0. If you wanted to graph this, you graph it in 2 different parts. You graph it in one part when x is bigger than 0, you make it equal to 1. When x is less than 0, and this is supposed to be an open circle, and this is filled in. And we want to find out what's the limit as x gets close to 0. Well, if we approach x as 0 from the left, we would say the y value gets close to -1. If we approach x is 0 from the right, we would say the y value gets close to 1. And since those 2 values are different, we say that this does not exist or is undefined. So you can write undefined, you can write does not exist. And if we look at all of our values, sure enough, numerically it says the same thing. As x gets close to 0 from the negative side, it stays -1 all the way. As x gets close to 0 from the positive side, it stays 1. And so this limit does not exist because they approach different values.